Hello everyone. So we already have started discussion regarding the system associated with sensors. So in our previous lecture we have seen the basic circuits associated with sensors. So one of the circuit that we have discussed is voltage divider, where you have two resistances R1 and R2, and then you apply voltage across this, say VCC, and this is ground, and then you replace one of the resistances with a sensor. So in this case the sensor is resistive in nature, so basically your sensor also acts as a resistor, and then based on your response you can take the V out to the next stage of your system. Similarly, we also have seen the Wheatstone bridge, and we have discussed the details associated with the same. So in this case also, if the Wheatstone bridge is balanced, you'll find that the potential VAB, if you consider this node as A, this node as B, if you apply potential across these two nodes, and if your R1, R2, R3 and R4 they are proportionate, then your VAB should be 0, right? So that is what we have seen in our previous lecture. Now as far as the sensor system is concerned, as we have seen that it has different components associated with it. So the first component was filter and then amplifier. Both these components are very important for signal conditioning. Now we will see what is an amplifier, and briefly we'll check how we can design an amplifier circuit, and then we will discuss what is a filter and different considerations related to filter. So this is the basic diagram of a amplifier. So amplifier usually has an inverting input, and it also has a non-inverting input, as it is shown over here. Then an amplifier usually has an input impedance which is very high. So this is an open loop operational amplifier. So in this case the amplifier that we are discussing is an operational amplifier. The input impedance of an operational amplifier is usually very high, and hence we consider there is no current that goes into the amplifier. So we can assume that no current enters into the amplifier because the input impedance is very high. Then there are supply voltages associated with operational amplifier, and then you have an output impedance which usually are very low. So output impedance of different amplifiers, different operational amplifiers, are low, and then you have an output voltage. So these are the basic details regarding operational amplifier. Two inputs, inverting input, non-inverting input. So inverting input is symbolized with a minus symbol, non-inverting input symbolized with a plus symbol. Then supply voltage is Vs minus Vs. Then you have output impedance which is very low in case of operational amplifier. And then if you look at the input versus output relationship, then you will find your output voltage is A times higher than the difference between input voltages, that is V2 minus V1. In this case the difference in the input voltage is V2 minus V1, considering V2 is higher than V1, and then the output voltage V out is equal to A open loop, which is a constant, into V2 minus V1. This particular term is known as open loop gain, open loop gain. So this operational amplifier has a gain, open loop gain, which is equal to AOL. Now you can connect different resistors and capacitors between input and output. So this side is input side, this side is output side. So you can connect resistors and capacitors between input and output for different operations. Now we will see how input and output, the resistance and capacitors connected between input and output will help us in designing an circuit. So the first example that we have is an inverting amplifier. Why it is inverting amplifier? Because we apply the input voltage in the inverting input, that is symbolized with minus symbol, and then we connect two resistors R1 and R2. R1 is connected with input, R2 is connected between input and output as it is shown in this figure, and then you ground the non-inverting terminal. Now because there is no current going inside the terminal, you can consider the potential V0 here is similar to the potential that you see over here. So this entire line has the same potential V0. So in this case, we also consider or assume that the potential in non-inverting terminal, that is here, is equal to the potential over here. So V0 is actually grounded because this terminal is grounded. That's why we call it virtual ground. No current is entering inside the operational amplifier. So whatever current is coming from the input side will directly go to R2 and then it will go to the output. So let us consider the current in the input side is I. So your I is equal to V in minus V0 divided by R1. Now because V0 is grounded, it's equal to 0. So you can consider this as 0. So the value of I is V in divided by R1. Similarly, in this case, if you consider the feedback, that is the resistor connected between input and output, we can call this as feedback loop. So in this loop also, the current is I1 as in I. Here we have considered the current as I. So the current will flow through this loop because no current will enter inside the operational amplifier because the input impedance of the operational amplifier is very high. So the current will go through R2. So in this case, you can consider I is equal to V0 minus V out divided by R2. Now again your V0 is 0. So you can consider your I is equal to minus V out by R2 as it is shown over here. So here minus I is equal to V out by R2. You can also consider I is equal to minus V out by R2. Now replace the value of I from this equation to this equation. Then you will find that V in by R1 is equal to minus V out by R2. So V out by V in is equal to minus R2 by R1. You take the V in over here, R2 over here. So you can also consider V out is equal to minus R2 by R1 into V in. I mean, you can directly write this equation from here. So your V out is equal to minus R2 by R1 into V in. Now what is amplification? Amplification is the ratio between V out and V in. Now this term is your amplification or gain. We can consider this as gain. So gain is something which says your output is how much times your input, right? So in this case, your V out by V in is minus R2 by R1. We call it as gain of this inverting amplifier. So for an inverting amplifier, the gain is minus R2 by R1. And why we call it inverting amplifier? We call it inverting amplifier because your output is negative if your input is positive, right? If your V in is positive, your output is minus something into V in. That means your output is negative. So it is inverting the input. At the same time, there is a gain associated with it. That means it is also amplifying the input. If R2 by R1 is greater than 1. If it is equal to 1, then there is no amplification, only inversion. And this will be equal to 1 when R2 is equal to R1. So if R2 is equal to R1, so then there will be no amplification. Your V out is equal to minus V in. That is, it is only inverting. Now in order to make R2 by R1 greater than 1, your R2 should be greater than R1. Then only you will get certain sort of amplification. That means your input will be amplified. So this is the circuit diagram of an inverting amplifier. Anyways, you have to put the supply voltages here. I am just showing the circuit that is responsible for amplification. Okay. So this is the inverting amplifier. Similarly, we will also find a circuit which is known as non-inverting amplifier. Now there are two things that we have considered. One is no current flows inside the amplifier, operational amplifier, and second is the potential here is equal to the potential here. If this terminal is grounded at this point, then we can consider a virtual ground in this particular point. Okay. Otherwise, the potential that you see over here should be equal to the potential over here. In case of non-inverting amplifier, we connect our input to the non-inverting terminal of the amplifier, and then you connect two resistor R1 and R2 the way it is shown in this figure. Now in this case, the current I that flows through R2 will also flow through R1 because no current flows inside the amplifier, so no current will go in this direction. Whatever current is coming should go through R1 only. So there is no current in this particular direction. Hence, you can consider I as V out. So in this case, again, this terminal is grounded. That means this part is also grounded, right? So sorry, this terminal is V in. That means here also it is V in. I repeat, this terminal is V in, and we have seen that this terminal and this terminal should be in the same potential. We consider that this terminal and this terminal should be in the same potential. So the voltage over potential over here also should be V in. So in this case, this potential also should be V in, and hence the I that is flowing through this loop should be V in minus 0 divided by R1. So it is V in by R1. Similarly, if you consider the entire loop, the total resistance RT is equal to R1 plus R2. Hence, you can consider I is equal to, at this point also the potential is V out. So it's V out minus 0 divided by R1 plus R2, right? Now replace the value of I from this equation to this equation. you will find V out divided by R1 plus R2 is equal to V in by R1. That means V out is equal to R1 plus R2 divided by R1 into V in. If you divide both the term with R1, then V out is equal to 1 plus R2 by R1 into V in. This term is the gain of the amplifier. So, as it is shown over here. So, your V out is equal to gain into V in. Now, in this case, this is non-inverting amplifier because V out and V in, if V in is positive, your V out is also positive. If V in is negative, your V out is also negative. So, it is not inverting the input. So, that is why it is a non-inverting amplifier, and this is the gain of the non-inverting amplifier. Similarly, with amplifiers, we can also create or we can also make different types of circuits. I will also show a few more examples so that it becomes clear to you. So, this is a summing amplifier. In this case, what you do is your target is to sum multiple inputs. For example, say in this case you have 3 different inputs V1, V2, V3, and you want a V out that should provide the summation of input. So, they are connected the way it is shown in the circuit. So, V1 is connected to a resistor R1, V2 is connected to a resistor R2, V3 is connected to a resistor R3, RF is your feedback resistor. So, RF is the resistor that is connected in the feedback loop, and this is again the inputs are connected into inverting terminal. Your non-inverting terminal is grounded. So, if this terminal is grounded, this part is ground, then this particular node also is in ground. We can call this a virtual ground. Now, in order to calculate the V output, what we can do is we can take help of superposition theorem, where we will only consider one input and will ignore other inputs. This will simplify the process. Now, in superposition theorem, if there are multiple sources, what we do is we consider one source at a time, we ignore the other sources, and then once the consideration for all sources are done, we add all these outputs for individual contribution in order to get the total output. So, here also first we will consider V1 only in the loop 1, and in this case if you do not consider V2 and V3, R1 is connected to inverting input. So, it is an inverting amplifier. So, you can write V out is equal to minus RF by R1 into V1. Similarly, now you consider V2, ignore V1 and V3. This again forms a inverting amplifier. So, your V out in this case will be RF minus RF by R2 into V2. V2 is input in this case. For loop 3, that is this loop, consider V3 and ignore V1 and V2. In this case, your V out is equal to minus RF by R3 into V3. Now, your total V out, you can consider it V out 1, V out 2, V out 3. Now, your V out, actual V out should be V out 1 plus V out 2 plus V out 3. Now, you just put all these values, you will find this is equal to minus RF by R1 into V1, RF by R2 into V2 plus RF by R3 into V3 according to superposition theorem. And then if your RF is equal to R1 plus R2 plus R3, then this is minus V1 plus V2 plus V3, because this will cancel out if you consider RF is equal to, it should be RF is equal to R1 equal to R2 equal to R3. Okay. So if your RF is equal to R1 is equal to R2 is equal to R3, if all 3 or 4 resistors are equal, then this will cancel out, and then your output will be V out is equal to minus V1 plus V2 plus V3, which is the summation of all inputs. So you can add more inputs here, V4 and so on. You will find that your output is nothing but the summation of all the inputs that you place if your RF is equal to all resistors that you connect over here. Okay. In fact, if you want to provide a certain gain to certain input, for example, say you want V1 to get amplified by 2 times. In that case, you can consider R2 is equal to, or you can consider RF is equal to 2R2. Then if you place this relation here, you will find V1 plus 2 into V2 plus V3. So in this case, your V2 will get amplified twice in the output side. So you have that control as well. So this is how you can develop a summing amplifier. Then there is a differential amplifier, which is very, very important. So in case of differential amplifier, the target is to calculate or amplify the difference between the inputs. So you connect 2 input V1 and V2. One is connected to non-inverting terminal, another one is connected to inverting terminal, and then you have a V out. Now let us see, if we connect V1 and V2 the way it is shown, what is your V out? In this case also we will take help of superposition theorem. That means we will ignore one input and consider the other. So we are going to take one input at a time. So in this case, to begin with, let us consider V1 and ignore V2. We know that no current flows inside the amplifier. So if the current in the input side is I1, then you can consider I1, for example, say here the potential is V plus. The potential in the non-inverting terminal is V plus. So here also the potential will be V plus. Now the I1 in this case is V1 minus V plus divided by R1. So this is the value of I1 as it is shown over here. Similarly, if you consider only this loop, then your I1 is equal to V plus minus 0, because this part is ground, divided by R2. So if this is ground, that is a 0 potential, right? So I1 in this case can also be written as V plus divided by R2. Now let us replace the value of I1 from this equation to this equation. You will get V plus by R2 is equal to V1 minus V plus divided by R1. Now let us rearrange this equation. Then you will find the value of V plus is equal to V1 into R2 divided by R1 plus R2. If you do simple rearrangement, you will find V plus is equal to V1 into R2 divided by R1 plus R2. So this is the value of V plus. Okay. Now let us consider the circuit which is associated, or we can actually ignore the circuit, this part of the circuit. So let us ignore this part of the circuit and only consider this part, because we now know what is the potential of V plus, or the value of V plus is known. And secondly, V2 we already have ignored in the first case. So your circuit will reduce to this one. Let us consider the V out in this case is V1 out. that is output for V1 only. Now we know V plus is equal to this, and if we consider this loop, we can write I is equal to V1 out minus 0 divided by total resistance, that is R3 plus R4. No current will flow inside the amplifier. So the current I will flow through I3 as well, right? So this is your total resistance and the value of I. Similarly, if this terminal is V plus, you can consider this terminal also as V plus. That means this node also has a potential V plus. So you can also write I is equal to V plus minus 0 divided by R3, that is V plus by R3, that is written over here, and I also is equal to V1 out divided by R3 plus R4, that is written over here. Now from these two equations, if you replace the value of I here with this equation, then if you rearrange a bit, you will find V1 out is equal to V plus R3 plus R4 divided by R3. Replace the value of V plus that we have calculated in the previous slide, it is also written over here in this equation, then you will find V1 out is equal to V1 R2 divided by R1 plus R2 into this term R3 plus R4 divided by R3. So this is the value of your V1 out, that is the output for V1 source. Similarly, let us consider V2 and ignore V1, then your entire circuit will reduce to this one, where if you take this loop into consideration, you can write the value I is equal to, for example, in this case the value input potential is V2, and because this terminal is grounded, so here we have both the terminals grounded, that means V plus in this case is actually 0, so this is also 0, this part is also 0 because of virtual ground. So your I should be V2 minus 0 divided by R3, that means V2 is equal to I R3. Similarly, if you consider this resistance only, then you can write your V2 out is equal to minus I into R4. Consider this one. Similarly, apply the similar concept. This part is 0, grounded. So your V2 out will be equal to minus I into R4. Now, let us put the value of I from this equation to this equation. Then your V2 out is equal to minus V2 into R4 by R3. Now you know what is the value of V2 out. Then your V out will be V1 out plus V2 out according to superposition theorem. So after applying superposition theorem, you will find your V out is equal to V1 into R2 divided by R1 plus R2 into R4 plus R3 divided by R3 minus this term V2 into R4 by R3. So this is what is your V out. Now let us take R1 is equal to R3, R2 is equal to R4 to simplify this equation. Currently the V out equation is bit complex. Now to simplify that, let us take R1 is equal to R3, R2 is equal to R4, and if you put these values in this equation, you will find V out is equal to V1 into R4 by R3 minus V2 into R4 by R3. Take R4 by R3 in common, you will find V out is equal to V1 minus V2 into R4 by R3. So in this case, your R4 by R3 is the gain of this amplifier. Now sensor with small differential voltage, for example say thermocouples, they need differential amplifier because they work based on small differential voltages across this sensor. So in such kind of sensors you need differential amplifiers. If you get a very small differential voltage, that is difference in voltage, you can adjust the gain so that you get an output or you get a desired output that you may use in the next stage of your circuit. So this is a differential amplifier, and this type of amplifiers are usually used for sensors that produces differential input. So this is something which is very important as far as the sensor system is concerned. In the upcoming discussion, we will discuss another very important amplifier which is known as instrumentation amplifier. Till then, thank you.